Let's review again what we mean by a simple random sample. So in a simple random sample, or SRS for simple random sample, every sample of the same size has the same chance, or the same likelihood, the same probability of being selected. So today in class, when we were doing the random rectangles activity, we have a population of 100 rectangles on the back side of the handout, and I wanted you to randomly select 5 of them. That's what this command does in the graphing calculator. So I'll just re-execute the command here, and I'll create a simple random sample where every sample of size 5, every sample of 5 rectangles, has the same chance of being selected. So I will select, starting with the integer number 1 and stopping with the integer number 100, I will select 5 of them. So here is a random sample where I selected rectangle number 95, number 91, number 15, number 52, and number 41. Now, if I press enter again, I can run the command again and I can get another random sample of size 5. So again, every sample of size 5 has the same chance of being selected. So in this sample, I got rectangle number 74, rectangle number 5, rectangle number 34, number 100, and number 21. So every group of the same size, of size 5, has the same chance of being selected. Okay, well, what if I did something different? So what if instead I used randomness but in a different way? So here, I want you to explain why this strategy is not a simple random sample. So I could randomly select one rectangle from number 1 to number 20. So to do that on the graphing calculator, from 1 to 20, I can select one rectangle. I got rectangle number 16. No problem. So I can randomly select one rectangle from 21 to 40. No problem. So starting with 21 and stopping with 40, I will randomly select one. I got rectangle number 40. And I can continue doing the same thing. So I'll select one from, randomly I'll select a rectangle from 41 to 60. This time I got 45. I'll select randomly a rectangle from 61 to 80. Rectangle number 68. And then lastly, from 81 to 100, I'll select one of those randomly. Got rectangle number 81. So here, just for kicks, we can even go look at our sample. 16, 40, 45, 68, 81. So rectangle number 16, let's find it. Here it is. Here's rectangle number 16. Rectangle number 40 is this one. Rectangle number 45 is this one. 68 and 81. So let's see, where is number 68? Oh, 68 is down here. It's this long one. Here's number 68. And rectangle number 81, right here. So there is a randomly selected sample of 5 rectangles, and I could find the area of those 5 rectangles, and then I can calculate the average of the areas of those 5 rectangles. I can do whatever I want with those 5 rectangles. But those 5 rectangles are a sample from the entire population of 100 rectangles. They were selected randomly, but they do not represent a simple random sample. So let me say that again. There are 5 rectangles here. We selected them randomly. We selected them randomly from this population of 100 rectangles. But it is not a simple random sample of size 5. So here's why. In order to be a simple random sample, every sample of the same size has to have the same chance of being selected. Well, here, using this sampling strategy, I can actually come up with a sample of size 5 that has no chance of being selected. Well, wait a minute. That means that we violated the definition of a simple random sample. To be a simple random sample, every sample of 5 has to have the same chance of being selected. Well, if I can find a sample of 5 that has no chance of being selected, where there are other samples that do have a chance of being selected that are that same size, well, then not all of those samples have the same chance of being selected. Some can be selected, some can't be selected. So this sample, 16, 40, 45, 68, 81, that sample had a chance of being selected. Well, I can think of a sample very easily that has no chance of being selected. Can I randomly get, using this method, can I get rectangles 1, 2, 3, 4, and 5? Well, no. Rectangles 1, 2, 3, 4, and 5 represent a sample of size 5 from the entire population, but using this random selection method, it is impossible to get 5 rectangles whose numbers are from 1 to 20. Now, the truth is, every group of size 5 should have the same chance of being selected. I can't get 5 rectangles from 21 to 40. I can't get 5 rectangles from 41 to 60. I couldn't get 1 rectangle from this group, 2 rectangles from this group, and 2 rectangles from this group. I can come up with all kinds of crazy combinations of rectangles that are not possible using this random selection strategy. So if I can think of samples that have no chance of being selected, if I can create what we call a counterexample, the truth is it's not a simple random sample. So for instance, the sample. So just for kicks, I'll use 2 rectangles from the first group. I'll use 2 rectangles from the second group. And then I'll use 1 rectangle from the last group. So here is a sample that has no chance of being selected. Is it a sample of size 5? Yes, but in order to be a simple random sample, in order for this method to represent the generation of a simple random sample, every sample of size 5 has to have the same chance of being selected. Well, here's a sample of size 5 that has no chance of being selected. This sample, 16, 40, 45, 68, 81, did have a chance of being selected. So here are 2 samples with different chances of being selected. This violates simple random sampling. So all you have to do to show me that something isn't a simple random sample is to write for me a counterexample. Show me a sample of the correct size that has no chance of being selected. We call that a counterexample. And that's good enough to show me that this method, or another method if you don't think it's a simple random sampling method, no problem. Show me an example of a sample of whichever size you care about. In this case, it was size 5 that can't be selected.